Welcome to Learn Robotics and AI. And in this video, I want to introduce you to the robot myCobot 280 Jetson Nano from the company Elephant Robotics. And we also have an adaptive gripper associated with it and a camera flange that one could attach on the end effector of the robot. So I'll be first unboxing the robotic system along with the gripper and the camera and all the accessories that are associated with it. And then I'll go ahead and actually demonstrate a simple, real world, practical project to show you how it is done on an actual robotic system. And in this project is that of image based pick and place. So it would take the image input from the camera and it would generate grasp poses and it would pick these objects and place those one by one. And this is the project. Without any further ado, let's get into it. Vision-based warehouse sorting. Here's what the layout of a simple warehouse looks like. We have a picking area marked in red. We have two warehouse tables and we have one waste bin that is marked in green, whereas the warehouse tables are marked in blue. What we want to do is we want to identify objects individually from the picking area, calculate their sizes, and based on the size of the object, we want to place it on one of the warehouse tables or throw it in the waste bin. So if the object is big, we want to place it on a warehouse table. If the object is small, we want to place it on warehouse table 2. However, if the object is larger than necessary, that is, it exceeds a certain size threshold, we want to throw it in the waste bin because it is a useless object. The robot is mounted on the left side of the picking area and is equipped with a camera and a gripper that is attached on the end effector of the robot. Let's have a look at the project pipeline. We have a picking area which contains all of the objects. We want to go to a position that allows the camera to capture a scene that contains all of the objects in our picking area. So we want to go to a look at position and capture an RGB image containing all of the objects in the scene, and that image would look something like this image that we see inside the picking area red square. And we want to detect all of the objects in the scene. And the way we do that is by using simple OpenCV commands. We would be first converting the raw RGB image into a grayscale image to reduce the complexity. Then we would be thresholding it, and then we'll be finding contours on this thresholded image, and that allows us to find different objects in the scene. So this is a simple way to detect objects in the scene. And what we would then do is, once we have identified the contours of all of the objects in the scene, we would want to find the object centers of each of these contours, and we want to then convert these 2D image positions to 3D grasp poses. And for that, of course, we need information from the hand-eye calibration. And the hand-eye calibration essentially performs a mapping between the 2D coordinates of each of the objects in the scene and converts it to 3D grasp poses that the gripper can understand. And once we have these 3D grasp poses, essentially we want to perform the picking operation, and then we want to place it at the right position. But in order to place it, we need to first get a sense of what the size of these objects are. And we want to calculate the sizes of each of these contours, which correspond to each of these objects. And we want to place these either on a warehouse bin, either inside a waste bin. We want to throw it in a waste bin if the object is too big. If it is of the right size, then we want to say whether it is a big object or a small object. If it is a big object, we want to place it on warehouse table 1. If it is a small object, we want to place it on warehouse table 2. So overall, the pipeline involves capturing the RGB image, finding the objects in the scene, determining the sizes of these objects, converting the 2D object coordinates in the image frame to 3D grasp poses, picking those objects and placing it on different locations based on the size. Now, what we want to do is a simple hand-eye calibration so that we know the positions of the object in the robot frame when we know the positions of the object in the image frame. So we want to have a mapping between the image XY coordinates of the object centers and the actual XY coordinates of the object in the robot base frame, because that is how we would be able to pick the object when we use these XY positions as grasp poses. So what we have are these two equations. We have the first equation, which is x position of the object with respect to the robot base frame, and this is equal to y position of the object in the image frame minus cy into ratio plus x reference. And then at the same time, we have y robot is equal to x image minus cx into ratio plus y reference. So there are a few terms that I would like to explain here. So there's x ref and y ref, and this is essentially a reference point that we have defined on the table, and you'll see it visually in a bit as well. So this is a reference point that is marked on the table, and we want to know the position of this reference point with respect to the base frame. So this is essential. And we also want to know the position of this reference point in the image frame, and this is represented by the points Cx and Cy. And I'll tell you in a bit how this is obtained as well. Then we have the other term ratio. Ratio is essentially the ratio of the distance between two objects in the real world scenario with respect to the robot frame and the distance between these two objects in the image frame. So to perform the hand-eye calibration or the simple mapping, we see that the robot goes to a look at point, and we see that there are 2 points marked. The first point with the circle in it is the reference point, and this corresponds to x ref and y ref. And when we place the object, we press enter, and an image is captured, and we are able to get cx and cy. And next, what we do is we place another object on the second point, and this essentially is used to calculate the ratio, and we are able to get these 2 points x1 y1 x2 y2, and we find out the ratio, and this is something that is used in the equations that we had a look at just right now. And if we look at the calibration matrix, we see that we have all of these parameters that are saved. So we have these three zones marked in red, blue, and green. The one that you see here is the warehouse table zone. We have two warehouse tables, warehouse table 1 on the left side and warehouse table 2 on the right side. Warehouse table 1 is a bit bigger than warehouse table 2, and it is used to place bigger objects, whereas warehouse table 2 is used for placing smaller objects. If the object size is larger than necessary, then we throw it in the waste bin that is marked in green here. So we would throw it here, and we can see that the picking area is marked in red, and it consists of 6 objects placed in random positions and orientations. And essentially, the camera would be going to a look at position, as you can see here, and then it would be capturing an image from the top view, and it would be identifying each of these objects. It would be finding the contours of these objects, and it would start picking these objects one by one. It would also be calculating the sizes of these objects, and based on the size, it would determine where it would like to place or throw the object. So it picks this purple object here, and then it decides to keep it on the warehouse table 1 as it is a big object, and it goes ahead and proceeds with picking the next object in our object list. And this is a simple safe home position that it goes to. Now it goes to pick a bigger object here, and the size of this object is essentially bigger than necessary. And this is calculated based on the area of the contour, and hence it throws it in the waste bin, and it goes to the safe home position again and proceeds to picking the next object in the scene. So it goes on to pick the black object here. And you can imagine that it being a small object, it places it on warehouse table number 2. And it continues to do it for the next object, which essentially is this complex object in the scene, and it essentially fails to pick it properly because it manipulated the position of the object as it was trying to pick. So uh, this is a bit challenging to pick as well because of the shape, and it has been placed in a random position, and that made it a little harder to pick. So it failed to pick this complex object in this case. Then it goes to pick the simple green cube, and it picks it successfully, and it decides to place it on the small table. As you can imagine, it goes on to picking the last object in the scene, which is this red object. And now you can probably make a guess as to which table or bin it belongs to. Of course, warehouse table number 1, since it is a bigger object. Now let's have a look at another demo with different objects and see how the algorithm performs. So we have these 6 new objects in this case. The image has been captured, and it proceeds towards picking the first object, which is a very small object with a complex shape. And it almost grasps it, but it fails because the gripper opening wasn't really large enough for this small object. And I could make it small, but then it would really make the grasping harder for other smaller objects which are a bit larger than this. So there's something that could be tuned, but it essentially fails to pick the first object. It picks the second object successfully, which is also a small object, so it places it on warehouse table number 2. And now going to the next object in the scene. Let's see which object this would be. We have a very flat black object. We have a red standard large object. We have this pink object, and we have this blue complex shape. So it picks the red object in the scene, and then it places it on warehouse table number one, which is correct. And proceeding to the next object in the scene, I think it will go to the black object and try to fix it, or no, the pink object, and it tries to grasp it, and it picks it successfully and places it on warehouse table number two. And now probably it will go to the black object, and I'm curious if it would be able to pick it or not. And it almost does. And I think again this is something I was a bit skeptical of because it is extremely flat. It's the gripper has to almost touch the surface of the table to be able to pick it, and it is a bit tricky to pick this object. Now note that it didn't really go towards picking the blue complex object in this case, because in this case it wasn't really detected in the object detection step itself, because uh, if you remember, we are essentially thresholding the image first, and then we are calculating contours. And since this color of this object is relatively light, I think it was probably not filtered from the rest of the background, and it wasn't really detected. So this object was not really picked in this particular case. Another demo, a different set of objects. So we can see that these are different objects, not the standard red cuboid in this case, but rather a purple cuboid, two complex green geometries, one really flat green surface, one small blue surface, and one black cone. So it picks this small green complex geometry, and it should place it on the small warehouse table, which it does successfully. And then it goes on to pick the slightly bigger green geometry, and it would place it on warehouse table number one as it is a larger object. Next, it goes on to picking the purple cuboid, which should also be on warehouse table number one. Let's see if it actually places it there. So this was a good pick, and it places it successfully on warehouse table number one. So far, so good. Now I'm curious about the lighter objects because they might not be detected at all because of because of how light the color is, and it blends with the rest of the background, which again could be tuned to make this work for these objects, but it can be a bit tricky. Okay, it does recognize the blue object, it seems, but it also kind of collides with the green plate and fails. I think if the green plate wasn't so close, it would have picked it. So it fails to grasp the blue object because it collided with the green object. If the green object wasn't there, the light green flat plate, I mean, if that object wasn't there, it would have successfully picked it and also placed it at the right position. And the green plate, it essentially didn't really recognize. So this, as I mentioned, has to do with tuning of the thresholding parameter, and this object is relatively light in color and it blends with the rest of the background considering the lighting conditions, etc. into a okay, one final demo showing a mix of different kinds of objects, some of which you have already seen now. So we have these three red objects of different shapes. One is the circular object, one is a complex geometry, and one is the standard cuboid. We have the purple cuboid, we have this green complex geometry, and we have this small green cube. So it captures the image and it starts picking the first object, which is this purple cuboid, and it manipulates a bit by going towards it, but it successfully picks it, and then it places it on warehouse table number one, which is where it is supposed to be. And now moving on to the next object, which is a complex geometry. Now I'm curious if it picks it up. This time it successfully picks it up. It seems to be relatively well oriented in this particular case. Um, it is a bit tricky in terms of where it is oriented, and it is a bigger object. It is way bigger than necessary, and hence it throws it in the waste bin, which is also absolutely correct. So far it's going pretty well. The rest of the objects should be pretty straightforward because we have seen the algorithm successfully pick these objects and place it at the right spot. So here, in this particular case, it picks this green object and it places it correctly on two warehouse table number one. Goes to the safe home position and then proceeds towards picking the green cube, which should be relatively straightforward, picks it up and successfully places it on table number two. And then it goes on to the red object, which should also be graspable, but it seems that it has been oriented in a position that makes it tricky to grasp it. And our gripper opening wasn't enough to accommodate for that. Now let's do a quick performance review of the myCobot 280 with Jetson Nano based on three specific criteria. Number one being motion smoothness, number two being speed of operation, and number three being accuracy. And all of these criteria are essential for a typical pick and place application, which is what manipulators are primarily used for. And if you look at the load test demonstration here, along with a lot of these pick and place demos that we have seen, the myCobot robot arm with the gripper and camera flange is able to follow the trajectories pretty smoothly, and it is able to repeatedly follow the same trajectory accurately. And if we look at the speed of operation, so I was operating the robot arm at a speed of 70 to 80 on a scale of 0 to 100, where 100 is the maximum speed of operation that the myCobot 280 is capable of operating on. Of course, for a pick and place application, I also need to reduce the speed a little bit so that it doesn't approach the object too quickly. And one could change the speed of operation using using the myCobot Python package, which is what I used in this project, and it is able to operate at really high speeds, high enough speeds for a typical pick and place application. So these two criteria are really good. And also in terms of accuracy, we see that it is able to repeatedly go to the same position accurately every single time for multiple different objects we have seen. And accuracy wise, it is also relatively good. What could be one critical aspect in terms of making it more accurate is how the gripper is mounted, because you can see uh, that it is mounted using these Lego style pins. And if there's play, or if the mounting is not so accurate or so tightly positioned, then it can really lead to slight inaccuracy. So these are some of the things that have to be taken into consideration if we want it to follow the trajectory smoothly, and if we wanted to follow the pick and place operation and reach the same target position every single time repeatedly and in a very accurate manner. So overall, it is a very good ARM for a standard pick and place application, which you can use for educational and research purposes. Now let's have a look at some of the features of the myCobot 280 Jetson Nano robotic arm. As the name says, it has Jetson Nano. It's also officially backed by NVIDIA. The robot is particularly designed for learning robotics and learning AI and integration of AI with robotics, etc., etc. So it has good ROS ecosystem. It has an open source library called myCobot, and this is essentially also what I use to build the simple image-based pick and place application project. And one could build more advanced projects with this robot. The myCobot library allows one to control the robot's end effectors. It has inverse kinematics functions. It has a lot of different classes and modules for controlling robots, for also moving the robots, for getting the joint states of the robot arm and performing several operations using the robot arm for pick and place, grasping, and general manipulation tasks. So its working radius is 280 mm and it has a payload of 250 gram. So you can only grasp smaller objects. However, for the size of the robot arm and with the adaptive gripper, it allows us to grasp these simple Lego pieces or small boxes, which are more or less sufficient if your goal is to build a simple application to help you make progress towards your learning goals as quickly as possible. So as I said, it has good ROS1 and ROS2 support, and it has user interfaces that it has provided. It has this software application called MyBlockly, which also allows one to program it using an interface, using a visual interface if you're someone who is not familiar with Python, but it is also supported with Python. As I mentioned, it has this library myCobot. It has USB, it has different ways of connecting to the robot, USB, Wi-Fi, Bluetooth, etc. It has this ROS support that one sees. And it also has a one-stop platform called My Studio. It has a test interface that one could use to essentially quickly test connectivity and do a lot of different things with the robotic system.
Okay, so hopefully you find this video valuable and you learned a lot about what it is like to work on an actual robotic system. We talked about a simple image based pick and place project using the myCobot 280. And of course, if you're interested in purchasing this robot, it is a really good robotic arm to consider purchasing if you're really serious about becoming a robotic software engineer and you want to gain your hands on an actual robotic system, to gain that exposure to build projects on an actual robotic system. So this is a really good arm to consider. There are links in the description that would direct you to purchasing the robotic arm. There's also a blog article that I've written that is corresponding to this video, where I have given details of all the components of this robotic system that we have talked about: the adaptive gripper, the myCobot 280 arm, the camera flange, how to mount those, etc., etc., and also a little bit about this project that we have discussed in this video. And lastly, if you are absolutely sure that you want to work at a robotics company in the future, and you know that this is your passion and you do not want to waste any more time, I would consider having a look at the course Become a Professional Robotic Software Engineer. I have spent countless hours designing this course and I have created multiple different iterations. I don't even have a count of how many times I have reiterated and improved upon this course, and I still improve and validate and verify this course again and again based on interactions with the students who are enrolled in this course. They find they derive a lot of value from this course, and I encourage you to have a look at this course, but only if you're really serious, because this course requires a significant amount of time investment, but it would give you the right structure and the roadmap and the right set of resources and technical content for you to get started with robotic software engineering and continue learning even after you get your robotics job, even after you get your first robotics job, because robotics is something that requires you to constantly learn new algorithms, new approaches, and new domains, and to enhance your skill set continuously. You would be given a lifetime access to the course. You'll be given a lifetime access to the course. You can access the resource, the monthly Q&A sessions or monthly meetups. You have access to the private accountability group and a lot of these details which I wouldn't go into. So if you're interested in learning robotics, check out the course, become a professional robotic software engineer.